All right. And what I'm going to do is share with you um, the ebook, first thing. And what I'm showing you now is in section 9.2, at the very end of the section. There is a section here on choosing the sample size, which is what most researchers will do before they conduct any research. They're going to be interviewing people. Then they're going to have to consider how many people to interview. What's the minimum size? And so what we do is we take our margin of error formula. This is it right here in the middle of the screen. M for margin of error is equal to the critical value. In this case, they put in 1.96, but that critical value, as I showed last time, is dependent on what the level of confidence is. All right, so this may change depending on the level of confidence. And then it's the square root, the square root formula here, which is the standard error. The standard error. All right, so it's a critical margin of error is always the critical value times the standard error. Now, if you want to find a minimum sample size, you have to choose an estimate for P, the portion. So it's something that a problem will give you, but if it doesn't give you that, then here's the rule. You use 0.5 for P, all right? So if the problem doesn't give you an estimate for P, use 0.5. All right. Critical value will depend on the level of confidence. So in this case, if it's 95%, it would be 1.96. If it was some other, if it was 90%, it would be 1.645, like that. All right. So you'd have to use your calculator. If you haven't already determined some of these confidence, these critical values, you're not sure what they are, you use your calculator, go to inverse normal in this case, because it's a Z. And remember, when the confidence level is 0.95, that's the middle part of the normal curve. So the area to the left of what you're trying to find, the critical value, is going to be the middle, 95% in this case, plus the left tail. The left tail in this case would be 2.5%. So it'll be 97.5%. But don't make that mistake. When you find the critical values, don't just put in the confidence interval value. That's not, it's never correct. All right, it's not 0.95. It's 0.975 in this case because it's the middle, which is the confidence level, middle value, the middle area, plus the left tail. It's always that. All right. So, but I know some of you are going to do it anyway, but I'm mentioning it to you so that you know that that's a clear mistake to do that. All right. Now, how do you come up with n? Solve for n. When n is inside a square root, you square both sides, and then you cross multiply and solve for n. It's the margin of error formula squared and solve for n, and that's what you get here. It's p times 1 minus p. There should be z in the numerator here. All right, it says 1.96. The book here is not doing a great job here. They should put z in here first, and just for you to know it's the critical value divided by the margin of error, and the quantity squared. So this whole thing is your n, sample size, and what you do is just plug in the numbers, and whatever number you get, you round up to the next whole number, and that is your required, or another name for it, minimum sample size. All right, so required sample size, minimum sample size means the same thing. It means the smallest sample that you should get, that you should interview, if you want to say it that way, so that you get the margin of error that you want, and also the level of confidence that you want. Okay, that's the whole idea. Now, once again, if p is unknown in the problem for a proportion question, use 0.5. That's what they did in this case here. But if they do give you an estimate for p, you plug it into for p, and then 1 minus p would be the other complement of that. Okay, any questions about that? All right. So again, this book doesn't do a great job in showing you the general formula. They should give you the general formula. They don't. But I didn't write the book. So it is. All right. and you just run through and see how they do it. And remember, the 1.96 may not be 1.96 if it's a different level of confidence. Another number there. And they're just showing you here an example where P, they don't give you what an estimate for P, and you just plug in 0.5. P and 1 minus. In a similar way, go back. In 9.3, there is also a minimum sample size when we're estimating, when we're having confidence interval for sample means. So you also have a same type of formula there. And in this case, here is our margin of error formula. Once again, for some reason, they just put the Z in here, 1.96. They should just put Z because 1.96 is only for 95% confidence intervals, all right? Another level of confidence, we'll have another Z. And it's really, I'm really peeved about this a little bit because I wouldn't have written the book this way. It just doesn't make any sense. But anyway, once again, it's the critical value times the standard error. Remember, the standard error for for sampling distribution of means is sigma, the population standard deviation, divided by the square root of n. N is the sample size. So again, if you want to solve for n, you square both sides, and you end up with this formula here. Again, replace the 1.96 with z. It should be z times sigma divided by n, the quantity squared. Once again, you plug in all the information, you square it, and you round up to the next whole number, and you get your minimum or required sample size. It's very easy to do. You just plug in the numbers. All right, and just look at the example that they give. By the way, when they talk about margin of error in a word problem, they may not say margin of error. They might say, I want to know the minimum required sample size so that my my estimate will be within 0.02 of the true population mean or true population, whatever. That 0.02, whatever they say with after the word within, that's the margin of error. All right, and that's it. That's how you do it. Look at the examples in the book. All right, show you how it's calculated. And they give you a example on the next page here. Now, by the way, you need an estimate for the population standard deviation when you do a sample size problem with sample means. And they give you this formula here. They say if they give you a range of possible values for the variable that you're looking at, what they tell you to do is take the range, which is the largest value minus the smallest value. So if they say the values for the most part are between certain numbers, subtract those two numbers, that's the range. Remember, maximum minus minimum is the range. Divided by 4, and that gives you an estimate of sigma, the population standard deviation. So that's what you plug into the formula for sigma. And once again, whatever z is determined by the whether it's 95% or 99% or 90% or some other percents. I can give you 88%, 92%, 96%, whatever it might be. Okay, so you find the critical value, you find an estimate for sigma, which again, if they do it this way, unless they give you they give you the estimate, but if they don't, they'll give you something like this, where they'll give you a range of possible values for the variable. Just subtract those two numbers, divide by 4. And the margin error in this case is 20, because they want you to find the, let's see, yeah, they say it should be the estimate should be within $20 of the actual population mean. So 20 is your margin error. So you put 20 in there. All right, and then in this case, they came up with the n is equal to 96.04. You just round up to the next number, 97. That's the minimum or required sample size. All right, that's it for that. That's chapter 9. I'll go to chapter 10. And chapter 10 is a very interesting chapter because it deals with real research, because confidence intervals are just estimates. They're not It's not the research question typically. The research question has to do with the variable, and basically a researcher may have some idea of what the value of a variable is. All right. So instead of estimating it, they'll want to they have a theory about it, and then they use the sample that they get to test to see if their theory or hypothesis is correct or not. That's really what this section is all about, and it's a very you may find this section difficult at the beginning because it's brand new. It's new, but believe me, this is probably the most elementary level of hypothesis testing there is. And you may think, my God, if this is elementary, I can't picture what something else might be. But it's not really bad if you actually study it and try to understand what hypothesis testing is. If you don't read the text here, if you don't read chapter 10 at all, if you just decide to blow it off, you're not going to really understand this very much. You really won't, because it's really a very sophisticated, it's the way I would describe it. It's a sophisticated way of examining data to see if your theory or hypothesis has enough evidence, all right, from the sample. And it's very sophisticated. It's based on some principles of logic, and again, if you're taking this course and you feel like I have to take it, but I don't want to do so much work, then you're really, it's going to be hard to do well in this section of the course, because you're just not going to be able to follow the logic if you're not going to put any time into it. So please put some time in this. Actually read this chapter, read it through, and it will be helpful to you. It really will. And I've created a video. I think I'm going to post a video. I did it last semester. Not for this course, but for another course. I'll have to review the video again to see if it's appropriate for this class, but it gives sort of an introduction to hypothesis testing. But what I'm going to go over today is really an introduction to it. We're not going to get into the nuts and bolts of how to do it until next week. And by the way, next week's it, as far as new information. So today, next week, Monday and Wednesday, we're done as far as new information. We're finished. Because the week after that, we have a review for the next test, which is on chapters 8, 9, and 10, and then we have our test. And then the week after that, which is that Monday, is your final exam, and you're done. So we don't have really much time left, and so really pay attention to this. And again, don't try to, today in terms of hypothesis testing, try to strain too much in terms of understanding it, because again, you should read the chapter, review the video. I have another video from last semester on this that's posted. That's actually, it's not from last semester. I don't have anything from last semester from this course, but I will try to post something for you, an additional video, which will go over this concept of hypothesis testing. All right, so let's talk about what a hypothesis is, first of all. It's a claim or statement about the value of a single population characteristic. Now, it's about the value of a population characteristic. In other words, a population mean or a population proportion. And by the way, that's it. There are many types of hypothesis tests for many different types of population parameters. Remember what a population parameter is. It is a mean, a population mean or a population proportion. A statistic is your sample mean or sample proportion. So the claim is always about the population. We're making a claim about it. We're guessing. It's a hypothesis. All right. So we might feel like the population mean is 1,000, or the population proportion is less than 0.01. Whatever it might be. It is a statement, and we express it in symbols. And that's actually what is required for this course, is to express everything with symbols. All right. So we have mu and p. Now mu, by the way, and I will show you probably next week, because for the final exam, there's going to be a portion of it. This is the core piece that the department has developed, the core part of the final exam. It's not multiple choice. It's not fill in the blank. You actually have to type in the answers. So I'll show you a little bit in Canvas how to type in a Greek letter like mu. You may have to type that in. So when you do hypothesis testing or display hypothesis tests, you have to do it symbolically. But I'll show you how to do that in Canvas again next week. All right. There are two hypotheses basically that are going to be competing against each other in a hypothesis test. One of them is called the null hypothesis, and the other one's called the alternative hypothesis. So two hypotheses. Now, the alternative hypothesis is typically the researcher's hypothesis. All right, that's what it is typically. And the null hypothesis is basically something like mu is equal to 1,000 or p is equal to 0.01. It's always equal to. There's always an equal to sign for the null hypothesis. There's some value that we're stating. Typically, it's a value that's considered to be accepted by the current researchers, something like that. And you're a trailblazer, and you come up with a different idea. You think mu is not 1,000. You think mu is less than 1,000 or greater than 1,000, or just not equal to 1,000, something like that. That's your alternative hypothesis. It's your research hypothesis. You don't think this mu is equal to 1,000 is correct. All right. So what do? You collect some data, you analyze it, and then you see if you are correct or not. That's really what we're going to be doing. So the null hypothesis is a claim about the population characteristic that is initially assumed to be true in general by the researchers or population, whatever it might be. All right, it's just considered assumed to be true unless we have enough evidence to show that it's not. All right, and we use this symbol here, H sub 0. H sub 0 as the symbol for the null hypothesis. All right, that's what we do. All right, and then the other hypothesis, the researcher's hypothesis, the competing claim, we can call it, about the population characteristic is called the alternative hypothesis, and we use the symbol H sub A. Obviously, A means alternative. All right. So when we carry out a test, we're going to have two competing hypotheses: H sub 0, which is the null, the accepted hypothesis, and your hypothesis as the blaze runner, the person who has the new idea. H sub A hypothesis. So these are going to compete, and you're going to see which one seems to be the better hypothesis in terms of the sample data that you've collected. Now, when you carry out a test, there are only two options. You're either going to say there's enough evidence to reject the null hypothesis in favor of the alternative hypothesis. And that only happens when the sample provides convincing evidence. The null hypothesis is probably, you can't prove it, certainly, but it can provide a lot of evidence for it. So there's convincing evidence that the null hypothesis is false. Right? We'll show you next week how that works. Now, if the sample does not provide such evidence, if there's not enough evidence to reject the null hypothesis, then the null hypothesis will not be rejected. Now, we won't say we accept the null hypothesis, because it is possible that because we didn't find enough evidence, it's still possible the null hypothesis is false. It's just we didn't find enough evidence to reject it. Okay. So there's two possible conclusions in a hypothesis test. Either we're going to reject the null hypothesis and claim that the alternative hypothesis is the better choice, or we could say there's not enough evidence to reject the null hypothesis. And so there won't be enough evidence to support our claim, our alternative hypothesis. All right. Now, the way to look at this, I don't know if the slides go into this very much, but let me see if they do. Let me take a quick look at this. Yeah, let me just tell you a little bit about an analogy to this. I don't know if any of you have ever been selected for jury duty. Anybody yell out? Tell me if you've been selected for jury duty. Anybody in class today? No. All right. You know what jury duty is? It's required. It's required. Wherever you live, you may be selected once you're old enough to vote. You're old enough to be selected for a jury. You'll get a notice in the mail, And guess what? You have to show up. You can't just throw it in the trash and say, I don't want to do it. No, it's required by law. You have to show up unless you have some really good excuse. It has to be a really good excuse. And anyway, there's two types of juries that you would be selected for. It would be a criminal trial or a civil trial. Civil trial would be something like, you're being sued for something or you're suing somebody. A criminal trial, I'm sure you've all watched television. Criminal trials are the ones that are more interesting for television. And so you've seen those types of shows about criminal trials. Typically, a jury is selected, typically 12 people, and there has to be a unanimous decision, right? Unanimous. So every juror has to be saying either their person is guilty or not guilty. All right. Now, in a criminal trial, I've been part of a jury in a criminal trial, and what the judge says to you basically is assume up front that the person who is being tried is not guilty. Assume they're innocent. All right, that's the initial assumption. So that's the null hypothesis. The null hypothesis is that the person is innocent. The alternative hypothesis is that the person's guilty, obviously. That's the alternative, right? So what happens during the trial? Well, the prosecutor gives you evidence, and you have to weigh that evidence, and according to the judge, it has to be beyond a reasonable doubt that evidence rejects the null hypothesis, that the person's innocent, and you therefore issue the judgment that the person is guilty. Right? There's enough evidence to make it beyond a reasonable doubt that the person's guilty. All right. So that's the level of evidence that's required. Now, what is beyond a reasonable doubt? That's something that the judge will define, but it's not mathematical. All right. There's nothing mathematical typically about it. So then the jury meets separately and they discuss it, and people have different ideas of what that might mean. But again, unanimous. It has to be unanimous. And then if it is unanimous, we reject the null hypothesis that the person's innocent and we convict them. If there's not enough evidence, according to the jury, then we do not reject the null hypothesis that the person's guilty. And of course, people will say, oh, I'm innocent. But we know that person still could have committed the crime. You've seen enough of these shows on television. The person could have committed the crime, right? So an error could be made. An error could be made by the jury. The jury could say the person's not innocent, okay? Or excuse me, that they're not guilty when they are guilty. It is also possible that the jury finds the person guilty, and yet they were innocent. We've heard of cases like that. So those are errors, and we're going to talk about those errors in a little bit. So a statistical test of a hypothesis test is just like that. We want to look at the sample data and see if there's enough evidence to reject the null hypothesis and go with the alternative as the better choice. It's the same thing, the same idea. Either we have enough evidence or we don't. If we don't have enough evidence, we don't reject the null hypothesis. All right. So I hope that analogy helps you understand a little bit about what we're trying to do. Now, the difference between a hypothesis test and a jury trial is that in a jury trial, there's some, it might be ambiguous in terms of whether there's enough evidence or not. Okay. It might be ambiguous. But in terms of, hold on a second here. Sounds like somebody's trying to get back in, but I don't see anything for them. All right. Now, that's the difference. The difference is with a jury trial, there's a debate among the jurors. All right, because some people say yes, some people say no. But in a hypothesis test, everybody agrees because it's mathematical. There are formulas that we're going to use, and everybody's going to agree whether there's enough evidence or there's not enough evidence. So it's not ambiguous. It's going to be clear, and there'll be steps that you will follow. All right, that's the difference. Statistical hypothesis testing, sophisticated mathematically, mathematical in nature, although the math is not hard. It's simple arithmetic. But it is, you should all get the same answer. All right. And if you don't, you made a mistake. That's all it means. All right. So, here's an example here. It says you have fluorescent light bulbs are more energy efficient than these compact ones, or more energy efficient than standard light bulbs. Okay. There's a brand called EcoBulb brand 60-watt light bulbs. They state on the package, the average life is 8,000 hours. All right. So the advertised claim by this company is that each light bulb will last for 8,000 hours. Obviously, people who purchase this brand would be unhappy if it lasted for less than 8,000 hours, right? If it lasted for more than 8,000 hours, we're good with that, right? But if it lasts for less than 8,000, we're going to be unhappy. So there could be some consumer group or somebody who's going to have a test to see if these light bulbs do last for 8,000 hours. And the alternative hypothesis is that the light bulb does not last for 8,000 hours. It lasts for less than 8,000 hours. You get the idea? So the null hypothesis is that it lasts for 8,000 hours. The alternative in this case is that it lasts for 8,000 hours, 8,000 hours, less than 8,000 hours, because that's what we're interested in, to see if it does. So then we look at the evidence. We collect a sample of light bulbs, of these types of light bulbs, and a random sample of them, and we want to see if the sample mean is so much lower than the 8,000 that we think there's enough evidence to claim that the true population number of hours for the light bulb is less than 8,000. So we would see if there's enough evidence to reject the null hypothesis that it is 8,000 hours, which is the advertised claim, and say, well, I think there's enough evidence to claim that it's less than 8,000 hours. Right? So that's basically the null and alternative hypothesis in this particular case. Right? Sort of makes sense. All right. So there's an advertised claim. There is maybe a group of consumers are getting together. They want to see. They think it's less than 8,000, and so they hire a research firm to test this out, and then the research firm will come to a conclusion. Again, the steps of how to come to that conclusion will be next week. I'm just giving you the language, the concepts of what hypothesis testing is today. All right, that's what we're trying to do. All right, and that's just a way of writing it, all right, symbolically. Okay. All right. So, hypothesized value is going to be a specific number. So we have to use the population symbol. If it's a mean, we use mu. If it's a proportion, we use p. And we're going to have a value, equal sign for the null hypothesis and some value. The alternative hypothesis has to have that same value. The values have to match. So the null hypothesis, the number that's after the equal sign, and the alternative hypothesis, those numbers have to match. Now, the alternative hypothesis is going to be one of three types. It's either going to be greater than that number, less than that number, or not equal to that number. And we're going to be using the following language to define these three types. We're going to call the first one a right tail test. We're going to, again, show you next week why we call it that. It's going to be called a right tail test because there's a greater than symbol here. The middle one, where it says less than, we're going to call that a left tail test because it's less than. And the one that says not equal to, we're going to call that a two tail test because not equal to means it could either be less than or greater than, one of those two. All right, so that'll become clear next week when we actually do examples of hypothesis tests. And I'll show you the 6 steps. There are going to be 6 steps to doing a hypothesis test, all right? This is Professor Barish's 6 steps of doing a hypothesis test. No matter what the book says, I'll show you the 6 steps. And I will test you on the 6 steps. So you have to know what the 6 steps are and how to do that. But this is going to be step number 1. of the 6 steps is defining the null and alternative hypothesis. And typically a word problem will give you enough information to put in the correct symbol, the mu or the p, and the value to the right of the equal sign and the value to the right of the inequality. All right. Now, one rule is that the null hypothesis will never have an equal sign in it. Excuse me, the null hypothesis will always have an equal sign in it. Always, it'll always be equal to. And the alternative hypothesis is going to be one of these 3 cases and will never have an equal sign to it. So for an alternative hypothesis, you will never see greater than or equal to, or less than or equal to. It'll always be either greater than, less than, or not equal to. Okay, so hopefully that's clear. All right. Here's an example with proportions. All right, so with a proportion, we're going to use the population parameter value P, or symbol P, for population proportion. We're saying in this particular case that the null hypothesis, H sub 0, notice it puts a colon afterwards, we put a colon after that, is P is equal to 0.1 versus the alternative that P is less than 0.1. All right. This is a left tail test. That's an example of, so the numbers have to match and the symbols have to match, and the symbols have to be population parameters, in this case, P for proportion. If it is a mean that we're testing, we have to use mu here. We never use X bar for means, okay? Now, look at this one here. We can't do this test because, can somebody tell me why we can't do this particular one? H naught mu is equal to 50 versus H naught mu is greater than 100. Why can't we use that one? Why is this wrong? This pair of hypotheses right here. This one from you.
The numbers are different.
I'm sorry, say again.
The numbers are different.
The numbers are different. And it sort of does logically, it makes sense, right? How can we compare mu is equal to 50 to mu is greater than 100? It makes no sense to do that. So we want to make sure these numbers match. All right, otherwise we'll have a gap between numbers and it doesn't really make any sense to do that. The numbers always have to match, right? Okay. All right. All right. So let me see if there's anything else here that you need to know, because we only have about 11 minutes left before I close. They just show some examples of how to set up the hypotheses. Here's another one here on this slide here. This is a right tail test because the alternative hypothesis is P is greater than. So notice that we're looking at proportions here. So the null hypothesis is that the proportion of successes for a new laser, they're calling a new laser treatment here, there's probably saying it's 85%. So it's 0.85. And we're claiming, and a new researcher is claiming that the new laser treatment is better than that. All right, it's better, it's greater than 0.85 or 85%. All right, so it does a better job. So that's the alternative hypothesis, is that P is greater than a 0.85, and that's called a right tail test. All right, and here's again a left tail test. This is another one. And again, you can read through the slides. These are just examples of the same thing. Now, one important point here, it says, is a statistical hypothesis test is only capable of demonstrating strong support for the alternative hypothesis by rejecting the null hypothesis. It doesn't prove it, it just gives you strong support for it. When the null hypothesis is not rejected, it does not mean strong support for the null hypothesis. It just means that there's not enough evidence to reject it. Okay, clear on that? All right, so let's go to the next section 10.2. All right, so let's share now on the other one. Now, I mentioned earlier, when I was giving you the example of a criminal trial, that mistakes can be made by the jury, right? And there's 2 types of mistakes. One mistake is that they reject the null hypothesis. In other words, they think there's enough evidence to convict the person, all right, of some crime. when in reality, they didn't commit the crime. We've heard of cases like that, people being in prison for 30 years, and finally some DNA evidence shows that they never committed the crime. It happens. It can happen. On the other hand, there are cases where a person is not found guilty of a crime at all right? And yet they did commit the crime, all right? There was a very famous, maybe you all know about it, you've heard about it before probably you were born, unless you're an older student. You probably heard about the O.J. Simpson case in the mid-1990s, right? Where she was accused of killing his wife and a friend of his wife, all right? And many people felt that, and again, it wasn't based on evidence, it was based on the way he behaved right after this crime happened. There was a chase, seemed like he was running away from the police and all of that sort of thing. But he was found not guilty, and that you have many people, not all people, but some people felt that they thought he was guilty. Now, was there enough evidence? Debatable, but he was found not guilty. But what if he did commit the crime? That was an error also. That's a famous case of somebody who was found not guilty, but many people felt like he did commit the crime. So anyway, regardless, those types of mistakes happen also. So that's what we're going to talk about here for the next 5 minutes or so. And this second, the errors in hypothesis testing, because that's important. It is possible we're going to make an error. Now, what we're going to be doing next week is we're going to do a test procedure. In other words, a step-by-step process through which we take the sample data and we determine whether we should reject the null hypothesis or not reject it. All right? This is a test procedure. Just like in a jury trial, the judge gives you a step-by-step process to determine whether the person is guilty or not. Except in this case here, there's, again, like I said before, it's not going to be ambiguous. It'll be crystal clear. If you're doing the test procedure correctly, it'll be clear whether we're rejecting the null hypothesis or we're not. All right, now everybody should come to the same conclusion. All right. Now, there are two types of errors that could be made. All right, and again, think of these in terms of this jury trial situation I just mentioned. One of them is called a type 1 error. Now, this type 1 versus type 2, this is just statistics lingo. Somebody made this up, maybe 50, 60 years ago, came up with this language. But just know that you have to sort of know this. Now, in the past, when you were taking statistics and you had to, you were taking a test, you'd have to have the professor might give you a form, let you use a formula sheet, and you would write this down on your formula sheet. But now that you are taking this and you don't have to have a formula sheet, you just make sure that you know where this is in your book, or even print it out, write it down, just have it next to you when you're taking a test for hypothesis tests, all right? Very important. So what is a type 1 error? This is the error when you've decided to reject a null hypothesis from what? From statistical evidence, all right? So you're going through the hypothesis test procedure and you believe there is enough evidence to reject the null hypothesis. However, in reality, and this is something we don't know for sure, because in reality, we don't know whether the null hypothesis is true or not, but let's assume in reality the null hypothesis is true. So we reject it, and yet it's true. That's called a type 1 error. And this would be the case like in a criminal trial, where we find the person guilty, but they didn't really commit the crime. All right, that's that type of error or mistake. And the type 2 error would be the case where we fail to reject the null hypothesis when the null hypothesis is actually false, when we should have rejected it. This is the O.J. Simpson situation I was referring to. And the jury did not find him guilty, but many people thought he was. Right? And maybe he did commit the crime. So that would be a type 2 error. All right. So you have to sort of know this right here. You have to see, if you see a particular situation, particular scenario, whatever you want to call it, certain word problem, you should be able to read the word problem and then put in your own words what the type 1 error would be and what the type 2 error would be. Now, there's no way of determining whether you have a type 1 or type 2 error, because unless you take a census, remember a census is you're asking everybody in the population for the answer, or measuring something, and would be for everybody in the population. So there's no risk. You'll be guaranteed to know what the answer would be, what the population mean is, or population proportion is. But again, we don't do censuses typically. We do a sample. So because because of sampling variability may not match the true population mean or proportion, there's always a risk that we are going to make an error. All right, always some risk. All right, so those are the two types of errors. All right, and then they give examples here. But let's look at this one example. Do we have time? Yeah, we'll look at this one example. So here's a pharmaceutical company, okay, and they issued a press release announcing that it had filed an application with the FDA, Food and Drug Administration, to begin some clinical trials of some experimental drug. All right, and what is the drug supposed to be doing? It's supposed to reduce the growth rate of cancer or tumors. All right. So, what is the null hypothesis? The null hypothesis is what we're testing is the mean growth rate of tumors without the experimental drug. That would be the null hypothesis. And the alternative hypothesis would be that the mean growth rate is going to be lower, or it says here the mean growth rate is lower without the experimental drug. All right. So it says here we can use mu to represent the actual mean growth rate of tumors for patients receiving the experimental drug. All right. All right. So basically, the alternative hypothesis is that the experimental drug will make the growth rate of tumors lower than it would be without the drug. The alternative hypothesis, the null hypothesis, is saying it doesn't make any difference. This drug doesn't work. The growth rate is the same as it was before. All right, get the idea? So this is a left tail test. And the question is, what would be a type 1 error in this case here? Well, let's say they go through the data, we collect sample data, and the type 1 error would be is that we find enough evidence to show that the experimental drug works when it really doesn't work. All right. In other words, the sample data seems to indicate that it does work when it doesn't work. What would be a type 2 error? Well, we're not rejecting the null hypothesis. So we seem to we don't have enough evidence in the sample to show that it works when in reality it does work. Get the idea? Those are the type 1 and type 2 errors. So that's really the examples that they're showing here in this section. All right. And let me just tell you one more thing, a couple more things. I'll go over this again at the beginning of the next class. But there are certain probabilities associated with these types of errors. The probability of a type 1 error is called alpha. All right. We use this Greek symbol alpha for it. And it's also called the significance level of the test. Don't worry about it right now. We'll go over this more next week. But it's the probability that we can have a type 1 error. That is, that we're rejecting the null hypothesis, and the null hypothesis is true. The other type of error, the type 2 error, the probability of that, we use the Greek symbol beta. That's the probability of not rejecting the null hypothesis when we should have rejected it. Now, type 1 error, very important for the rest of the course. Type 2 error, we don't really put too much emphasis on it because it's a little complicated. However, you do need to know these definitions, the definitions of these two things. And again, we'll talk more about this next time. Now, I think we just ran over just by 1 minute for the quiz, but you should be okay. So everybody can now open up the quiz. And again, it's on chapters 8 and 9, so make sure you have that information all ready to go. And give me a thumbs up if you see it. The quiz number, you see it? Great. All right, so you may begin. And again, hopefully you'll all have enough time to do this. If you run into a little problem at the end, I might give you a couple extra minutes. All right, so I'm going to put myself on mute. If you have any Issues, please send me a chat message.